Now, okay, we're all set. Now I'm going to go ahead and go over the problem you guys are asking. All right. So let me check it out real quick. This is number, you guys want to see number 3 on the homework set. Is that a 2-74? Does anyone know? Does anybody? I'm not. Okay. Can anyone describe what the problem is?
It has to do with the efficiency of a turbine generator.
Okay.
Is it 295, Professor? 2-95.
295. Okay, thank you. Let me see. Efficiency of a. All right, here it is. Oh, and okay. It's not the brick wall, is it?
No, it's
Okay.
it has like a reservoir, I think.
Okay. Here, let me do something here. Let me see if I have my beach board. All right, so let me just get it right from our site. All right, I guess I'll just open it. Is this it here? Or is the next one? Let's see.
It's the last one.
That one.
Oh, so you're asking, so someone's asking about this one? Okay.
Yes.
All right, so this one, all right. I mean, I can entertain some ideas here. All right, so what we're doing is it says the inner and outer surface of the brick wall are maintained at a constant temperature. All right, and the temperatures are given. So that is constant temperatures here. Let me go ahead and do something here. I'm gonna snip this and then paste it so it's a little bit quicker. All right. All right, so it's telling us that that this is a constant temperature as, let's see if I can, oh, you know what, I don't have my pad, my sketch pad connected. All right. You find my mouse here. Oh, here we go. Okay. All right. So it's saying that it's held at constant temperature, right? One side's at 20, one side is 5 degrees. And again, it's asking for what? The heat transfer rate through the wall is to be determined. All right, so we need to find the heat transfer rate, Q. So Q is equal to the thermal conductivity of the wall, which is given right here, Ka, the area of the wall, which you can get from the geometry, divided by the length. Some people use L, you can use X, is basically the length here. Is given here, right? And then times the change in temperature. So I would just say just delta T. Okay, so you have, what do you have? You have thermal conductivity. You have the area, right? Because we have geometry. Don't we have the area? Yeah, it's a 6x5 wall. You have the path, the thickness that it has to travel through, the heat. So we're trying to find the heat transfer through this wall. And now you have the change in temperature. Any other question on this? Because I think it's pretty straightforward. You should get your answer should be in kilowatts.
Yes, Professor.
Yeah.
For the change in temperature, do you go from, like, would it be like 5 minus 20?
Oh, I see what you're saying.
One end to the other?
Yeah. Usually, that's a good question. So really the the direction doesn't matter because we're only dealing with just with one. We're not dealing with multiple, like heat is escaping here, heat's works coming in. Because it's just one, we're asking for just the heat transfer, then it doesn't really matter. Typically what I do for delta T, and this is just basically a sign convention, I just say is T hot or T high minus T cold or T low, okay? So you can use that, and that'll give you, obviously it'll give you a positive value. Sorry guys, let me go in. I think someone's waiting in the lobby. Yep. All right. So that'll give you a positive value, but if you put negative, whatever the value is, I'd give you the correct answer anyway. Okay. All right. Anybody have any other questions or?
Thank you, Professor.
Okay, you're welcome.
The reason we use that equation is because it's conduction?
Yes, this is, yeah, this is conduction, exactly. Right, so that's the equation for conduction. Remember there was 3 equations for the 3 different types of heat transfer: conduction, convection, and radiation. So this is conduction. I'm not sure if that was specified, but conduction, remember, is when you go from you're traveling through a median, and it's basically just solid to solid. In this case, well, we don't know where. We just know the heat is traveling through the brick wall. There's only one piece here. So it's just solid. So if you're dealing with just solids and you have temperature difference, then yeah, it's conduction. If there was air blowing on one side and you were given some kind of a heat transfer coefficient, then that would have been convection. All right. Okay, very good. So yeah, the homework's due tomorrow, I think, right? At whatever time I put in there. I think I put 7. No, I think I put 11:59 p.m. just so that you officially turn it in before the end of Wednesday. Okay. Now we get to start chapter 3. So here's the title: properties of pure substances. So you guys know that you can get the lecture notes right through Beachboard. Because at first I was posting them here in Teams, but I mean it's probably just best you just get them here, going through our lecture notes. You got all the lecture notes here. We go in order: 1, 2, 3, 4, 5, except for the very end, 7. Here I skipped actually chapter 9 and 10, or I skipped chapter 8 and 9. I don't plan on doing that this year. This is because of the COVID and all that. It just kind of threw us all off. So. I think, or there might have been some. I might have been sick, but anyway. So here are the lecture notes. Going back. All right, properties of pure substances. All right, so the when you think of pure, don't necessarily think of elemental. I'll tell you what that we're talking about here. So the objectives is we're going to introduce the concept of pure substances. We're going to discuss what phase change is and the physics of phase change. We're going to illustrate pressure versus volume, temperature versus, well, actually specific volume, temperature versus specific volume, and pressure versus temperature diagrams that we use, that are commonly used to describe pure substances. We're going to demonstrate the procedures for determining thermodynamic properties of a pure substance. We will talk about ideal gas a little bit. Everything we do here is going to be, this chapter is ideal gas space. We're not going to deal with real gases because there's not really enough time to go into depth. And that's it. All right, so a pure substance. What is a pure substance? A pure substance has a fixed chemical composition throughout. So what I mean by elemental is don't confuse it with an elemental process, right? Sorry. So nitrogen is elemental, so it's only made out of nitrogen molecules. It's an N2 in its gas form. While air is not just made of one element, it's made out of several, but the primary ones are nitrogen and oxygen. But it's still considered a pure substance because because it has a fixed chemical composition. In other words, if I heat this air up, the oxygen doesn't separate from at least what I mean by if we heat it up in the temperatures that we work with, the oxygen and the nitrogen won't separate. All right, so that's why we call it a pure substance. So if that happened, if the nitrogen came out of and the oxygen stayed, then we wouldn't have a pure substance anymore. Then this is what we mean by change in state, liquid to vapor. When we heat something, we heat a liquid, basically starts to produce vapor, and the more the hotter we bring it, above its boiling point, we start to lose the liquid and start to gain in vapor. All right, I'll be writing some stuff up right now, but right now I'm just kind of giving you, this is a little bit easier for me to just conceptually talk about this. All right. So we know that solids are composed of molecules with bonds, and the bonds can be modeled like springs. And so what happens is when you agitate the solid, the springs start to vibrate, and that's basically analogous to temperature, right? The hotter you bring something, the hotter you get a solid, the more it vibrates, and these little molecules start to bounce back and forth, back and forth. So when we go, so that's going from a solid to a liquid. When we have a liquid, now what happens? We put enough energy so that we start breaking the bonds, and now, but there's still kind of molecule to molecule interactions and these things called van der Waals forces and things that kind of cluster the molecules together. And so this is a liquid. And when we go from solid to liquid, and then we put even more energy to the point where we just break them apart and they're no longer have enough, they have too much energy to be next to each other, then this becomes a gas. Right, so that's how we have that's what's happening at a microscopic level, solid, liquid, gas. All right, if there's any questions, let me know. We're not going to get we're not going to get it at all into molecular chemistry or anything like that. All right, now we're going to talk about phase change. This is where I'm going to start to start writing. All right. All right, so let me get my notes in front of me. All right. Okay, so phase change. Hold on a second. Where's my pen? Okay, something's wrong with my. Pen's not working too good. Okay, stand by, guys. Hold on a second. Okay, that's not good. All right. Okay, well, something's wrong. I'm gonna have to just go off of the charts here. I really apologize. I don't know what's going on here with my. Let me see if I disconnect and reconnect it. All right. Okay. Not working. I have another pad, surprisingly. Let me get the other pad real quick. There might be something with there might be some lag or something in the system. Okay. All right, here we go. Yeah, something's. All right, so let me go real slow here. And maybe I might have to just go and copy some sections here. So I'm going to go ahead and copy these two sections. That way I don't have to draw so much. All right. All right, so let's suppose that we are, okay, we're going to talk about state one. We have a pure substance that's inside this. This pink material here is a pure substance. Let's just assume it's water. Okay, let's go ahead and just call it water for now. So this is water we're going to put inside this piston. And we have a candle here. We have a sealed piston. There's nothing could escape out of the sides. We have temperature here at 20 degrees at 1 atmosphere. So at 20 degrees C and 1 atmosphere, we know that water is liquid, right? So this is liquid. Yeah, I wonder what's wrong with this pen. Or must be lag or something in the system. Anyway, I'm trying to draw liquid. All right. So there's liquid in here. And now let's suppose that sometime later, we go over here, and sometime later we have, we now take the temperature up to 100 degrees, and it's still 1 atmosphere. Let me describe what's going on. So this is frictionless. Anyway, frictionless. You know what? Hold on. Might just be better just to do this. All right. So it's a frictionless piston. And so therefore, pressure is always constant. Pressure is always constant because what happens is when we heat the gas up or heat the water up, and we know that water will expand when heated, then we know that this piston just basically just goes up. So it basically just goes up. It rises, right? So if you can look from left to right, you can see that the piston went up a little bit, and so it's basically because now we're, the water is starting to expand, and so instead of, if it was locked in, then the pressure would go up. If this was a rigid tank, then the pressure would go up. But because this is frictionless piston, it would just rise, and so therefore we got 1 atmosphere. Okay, so keep these states in mind. We started state 1 here. Pressure is equal to 1 atmosphere. Temperature is 20 degrees C of the water in a pistonless cylinder, in a frictionless piston cylinder. And state 2, we have again, we have 100 degrees now and 1 atmosphere pressure. Now we know what happens with water at 100 degrees, right? So this is at the point we start to vaporize right here. We start to vaporize the liquid. So so at 1 atmosphere and 100 degrees C, water exists as a liquid that is ready to vaporize, saturated liquid. All right, so we're going to use this a lot through this section here. Saturated liquid. All right, so we told you what the definition of saturated liquid is. It's right before you start to boil. Right. So if you can imagine, there isn't any little bubbles yet. It's right. You take it to 100 degrees. You don't agitate it, and that means the water is just a tenth of a degree or a millionth of a degree more, and this thing's going to start boiling. Or any agitation to the tank, it'll start producing bubbles. All right. So this is right before that. Right before that happens, we call that saturated liquid. All right. Next slide. All right. So apologize, I'm doing this. Again, I don't know what's going on with my pen, but maybe this is a good thing because this is probably more clear. All right, so now we are, so you got that, right? State 1, state 2. Now we're in state 3. Here we are. State 3. Okay, state 3. Now, what happens is, it says, let's read it. So saturated vapor is about to condense. Vapor that is about to condense. So basically in the world of saturated liquid, right, the next stage is saturated vapor. So saturated liquid is basically, it's the liquid, so it's the water in liquid form, but right before it boils, right? So right before it boils, and then saturated vapor is now it's the other side of that. So right, so it's basically right when the water first starts to boil, becomes saturated vapor. So what happens here is just say, so we're at state 3. We basically just left the candle at the bottom of the piston, and we're still at 1 atmospheric pressure. If you noticed from the previous pictures, the piston has started to go up, and so it's compensating for the rise in for the creation of saturated vapor. So see all these, this pocket here, this is composed of saturated vapor. Right now, a little bit less than 50% by volume. But we're still at 100 degrees C and 1 atmosphere. And you guys understand why we're still at 100 degrees C? We don't have this isn't climate control. This is not temperature control, right? Oh, I can't write. This is not temperature controlled. So Mother Nature has her own temperature control. Right? The temperature control here is that when water boils, its temperature is constant until every last bubble boils, assuming the pressure is constant, which it is here. So at 1 atmosphere, water boils at 100 degrees C. So it's, again, Mother Nature's own temperature control, and we have actually used this in a lot of space applications. A lot of applications, we use the fact that water changes phase as a way of controlling temperature. So if you want to keep something at 100 degrees C, right, you just boil water over it. Right, and you'll maintain it. You don't need any fancy temperature control equipment. Or if you need another temperature, just say you want to keep something at 75 degrees C Celsius, then you would boil ethanol, and so forth and so on. You would find different temperatures that have different boiling temperatures at 1 atmosphere. Okay, so what's going on? This is just telling you time is passing us by here. Wow, this is horrible. Let me type here. So time is proceeding, right? And anyway, and then so now we go to state 4, and what's the difference between state 3 and state 4? All right, so at state 4, we're still, lo and behold, we're still at 100 degrees C and 1 atmosphere. So before I go let me go back to state 3. All right. So we made a definition here. This vapor pocket is basically saturated vapor. All right. That's vapor that is 100 degrees C. So this is important. So I'm going to write this down right here. Saturated vapor is at 100 C. 100, I'm going to say 100 C. Okay. Saturated liquid is also at 100 C. So that's why we call it saturated. If the vapor somehow took off and started going above 100, say 200, 300, we call that superheated vapor. We're going to cover that in the next slide, or actually in this slide. But saturated means it's basically right at its boiling temperature. Okay, saturated liquid, saturated vapor. All right. So now we go here, and at state 4. Hold on, guys. Okay, so now we're at state 4, and now what happened is all the liquid, we're at the point where we just vaporized that last drop. So we had like one little bit of liquid left, and I can't even draw a little dot to indicate that. But anyway, Imagine there's just one little liquid left, and it just right now we just vaporized it. State 4. This now we're in state 4 where we have 100%. All right, so now we have 100% saturated vapor. So that's 100% saturated vapor, that volume right now. It's still 1 atmosphere. So basically states 2, 3, and 4 have all been 1 atmosphere and 100 degrees Celsius. Basically, we're just going through the beginning of boiling. State 3 is state 2 is the beginning of boiling. State 3 is basically halfway through the boiling. State 4 is we just boiled the last drop. We're at the end of boiling. And now that leads us to state 5, right? So state 5 now is we start to, we get superheated vapor. That means that's the reason we get, what we mean by superheated vapor is vapor above boiling temperature. So superheated vapor is vapor above boiling temperature. And what happens is we don't have the magic of phase change to keep us constant at 100 degrees anymore. So when we boiled when we had that last drop vaporized, now we don't have phase change anymore. So now there is no thermal control. And so it's in the sense we have gas. We just have pure gas that when the more heat that we apply to it, the more the hotter it gets. We're still at 100. We're still at 1 atmosphere. We're still at 1 atmosphere, but now we're starting to take off. All right. All right. So now what? All right. So let me go ahead and how does this look like on a temperature versus volume? On a temperature versus volume curve, it looks like this. I'm just going to take a snapshot of this so I can write over it. All right. So it says if the entire process, so the entire process between state 1 and state 5 are described in the figure below. All right. So again, we have we have state in here, and in state 1, you remember we had that the temperature was equal to 20 degrees C, and pressure was 1 atmosphere. It's a 1 atmosphere throughout, but anyway, just letting you know that. Now for state 2, state 2 is here. This is where we start in state 3 and state 4. This is where we have the 3 states with the same temperature. So for all these, we're going to say T is equal to 100. T is equal to 100 C, P equal to 1 atmosphere. So this is for all states, right? For 1, 2, and 3. So this is for 1, for 2. I'm sorry, for 2, for 3, and for 4. Right. And then, sorry, I keep hitting escape and it erases the last thing I did. What I have to hit is enter. All right. Now state 5 is different, right? State 5 is where we start to have the runaway condition. So the temperature is now 300. And the pressure is still 1 atmosphere, but we don't have the protection of we don't have the thermal control of phase change anymore because now it's just gas that we're heating, and we call that superheated vapor. All right. So this is how. Again, this is a diagram. This is basically if you map or if you graph temperature versus volume. Now this is V, but it's little v. Let me just say little. Let me do it in blue because it's in blue. Little v is specific volume, which means the units are it's meters cubed per kilogram. Right. So it's the inverse of density. So it's meter cubes per kilogram. And get used to that. Okay, it's still volume. Volume is volume. It's meters cubed, but it's just not per unit kilogram. Get used to doing this. Doing specific properties so that are divided by kilogram. Because now, if we divide by kilogram, now it doesn't matter what size of a system no one at all right now. No one's saying what's the size of the cylinder. Could this analysis pertain? Can we do the same analysis for a very large scale jet turbine generator versus a little benchtop little micro generator, something like that? Yeah, the same physics apply, and the way we get around that is we basically look at specific properties that are independent of kilograms of mass, right? So now when we do our analysis, we're looking at per kilogram. And at the very end, we say, well, how much mass are you? How much mass is experiencing this temperature change? And then that's when you multiply by mass. And that's when you get okay, this is, 200, 340 kilowatts. Or if you have a small system, you multiply the mass might be just milligrams, right? And then, this is, 50 milliwatts, right? So you bring your mass later to the party, right? You analyze the problem, and then at the end, you bring the mass. All right, so
Professor?
Yeah, go ahead.
I just had a brief question. So in this specific example with the frictionless piston, the pressure would never change, right? Because as the gas got hotter, the piston, it would just keep expanding, right?
So you're talking about the
pressure.
Yeah, the pressure would never change, right? It would just expand. Exactly.
Okay, just making sure I understood that. Thank you.
Yeah, you're welcome. Okay, so I'm gonna leave this slide up. You erased all the verbiage on purpose because I think, right. So the next slide is the pressure versus temperature. Now in this class, we don't use this that often. Pressure versus temperature, but this is what it looks like. So you basically have, if you multiply, so we were at 1 atmosphere. So in kilopascals, that would have been like 100 and, down here, like 101 kilopascal, 0.3. And so then you would have, right here's your temperature, right? So it's at 100. So that basically says that boiling happens for 1 atmosphere, which is 101, which is right here. It happens at 100 degrees C. Right, so that just shows you that. And so what happens if we increase the pressure of water? So just say we didn't have a free piston that moved up and down to compensate for pressure. In fact, we just clamped it down, or we torqued it down to where we pressurized the water. So if we added pressure to the water, obviously the water boils at higher temperatures. Look at 150 degrees C, we would require a pressure of something close to 500 kPa, or close to 5 atmospheres, or 5 times the atmospheric pressure. Okay, so keep in mind pressure. Boiling is a function of pressure. Right? What temperature water boils? Everything, the 100 degrees that we've been telling you right now, that only applies to 1 atmosphere, which is 101.3 kilopascal or 14.69 psi. At different pressures, boiling will happen at different temperatures. So can we say the same about freezing? If we does water freeze always at 100 degrees? Well, I don't know if that's a good way of looking at it. Okay, so can pressure, let me ask you guys this. If we lower the pressure of water, can we get freezing to happen below 0 degrees Celsius? So here we're raising the pressure of water, so that the boiling temperature rises, right? For 200 degrees C, it's probably past, it's like 800 kilopascal. So by the same method, if we lower the pressure, if we go, just say well, this doesn't make any sense, right? So we can't have negative pressure, right? So at zero pressure, so this is can we trust this origin right here? In other words, so let me just back up. Yes, at 0 pressure, we get 0 degrees C. And because we can't have negative pressure, then we can never, water will never freeze. Let me back up. The freezing temperature of water below 0 degrees C. All right. Now, a lot of people get that. I mean, even me, I think I realized this for the first time maybe 12 years ago, before I started teaching thermal. Is I had assumed that, like on Mars, for example, Mars has a very thin atmosphere, so the atmospheric pressure there is very low. It's something like, so here it's 100 kilopascal. On Mars, it's like 0.8 kilopascal or something, or actually, I think it's less than that. It's like 0.6 kilopascal. So it's 100 times less than Earth. But it turns out that water still boils at 0 degrees C. So water will and actually we use that fact to calibrate to calibrate instruments, right? We know that water is independent of pressure for its freezing. Now you can get water to freeze at different temperatures. That's fine, but the freezing temperature of water is still 0 degrees at 0 pressure in a vacuum. And it's for any pressure, actually. It's always 0. So even if we compress water many times over, many atmospheres, it still freezes at 0 degrees C. So it works the other way around. Now there is something that happens up here when, actually I take that back. If you go somewhere above, I forgot what the pressure is, but if you do get to a certain pressure, water will liquefy. So if you start off with frozen water, it will liquefy at a certain pressure, even if you're -0, if your temperature is negative. And all I know is that's, hey, I didn't know I can do this. Hold on a second. Holy smokes. Okay, I thought this was PDF. Okay, no, it's an actual. All right. So so that's the reason glaciers move, right? If you think about it, glaciers, like the bottom of a glacier is not going to be above 0 degrees C. It's below freezing, but so it's frozen. But when the pressures get so high, the water doesn't heat up. It just morphs. There is a transition. There's a phase change that happens, and it's and I forgot. It's called delta. It's the delta conditions way up here, and that's why glaciers will move. Okay. All right. So let's look at this. Maybe I can do this. Copy. Maybe if I can paste this over here. Oh, nice. All right. So this graph here on the right basically tells us, all right, that's fine. For I gave you this here. This on the left. So this is temperature versus volume, but it's for pressure is equal to 1 atmosphere. 1 atmosphere, which is equal to let's call it 0.1 megapascal. It's actually a little. It's 0.101 or something, but let's just say it's 0.1 megapascal, 1 atmosphere. This graph that we drew with the states and everything. All right, so now on the right basically tells you. It tells you, well, what if we went, so we go a point, how about we go a point instead of 0.1 megapascal, which is this line here? How about we go below that, 0.01, 10 times, so this would be pretty close to Mars here. So on Mars, your 5 points that we drew would look something like this. Obviously the boiling temperature would be much lower, right? So up here in the second graph from the bottom, this straight line here is 100 degrees C. I wish I can draw, but I can't. I know my stupid pen here, or my computer, it's actually my computer, is not allowing me to draw, but maybe I can draw. So we know that this is, right there is a certain temperature. This is a certain temperature right there. But we know that this one is 100, right? Because this one is what we just on the left hand side, that temperature. So this one below, I don't know what that is, but it's something lower than 100. And so if we raise the pressure, so now we're at, so this 3 from the top here, we're at 1 megapascal, so that 10 times atmospheric pressure, right? And so now the temperature here is probably, what did I say? It's 1 megapascal. It's probably, you know, it's, I don't know what it is, maybe 200 and something. So as we raise the pressure, these are our, again, our five dots, right? We the first one was down here somewhere 20 degrees C, and we had state 2, state 3, and, well, actually state 2, 3, wait, 2, 3, 4, and 5. So what happens is we're starting to form some kind of a bell-shaped curve type of thing as pressure goes up, right? So hold on a second. As pressure goes up, right, we start to form this bell-shaped curve. So let me draw that in a different. Looks like this. Ah, boy, horrible. You know, what if I getting frustrated here? What if I cheat? All right, check this out. Okay, so it starts to follow this kind of format, but this is even wrong here, because what I want to do is I want the I want this to kind of skew to the left a little bit. So what I want is a curve that where basically to the right of this blue curve, that's where boiling happens, right? So the temperature starts to take off. So it's flat, flat, flat until you hit the curve, and then the temperature starts to take off. Right here, I missed it a little bit, but flat, 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 and then it takes off. Flat, flat, and then it takes off, right? So what happens is we're forming this curve here, and this is called the saturation curve. Okay. In blue. So this is a saturation curve, and so what we do is the back of the book has well, in the back of the book we do have in our textbook, we use these values. So we need everything under this curve and everything outside we need access to. We need to be able to know when the temperature as a function of volume, a specific volume for water, in order for us to solve problems. And so instead of drawing a curve for each pressure, right, we have the back of the book, we actually have curves. I don't have them ready to show you right here, but we do have saturation curves. It looks like a big spider web. It's really hard to read. So instead of that, we have tables, right? But we use tables. So these are found in appendix, and this, I mean the curves of our book. However, we use tabulated values. Sorry, I'm trying to type sideways, so it's kind of in table format. So in the back of the book. All right. So if you went, I know I put them here. If we go to our site here, we have tables and beach board. And if you click on it, these are our property tables, right? And so what we do is we use a lot of water. So that's A4 saturated water temperature table, saturated water pressure table. A6 is superheated water. So this is where the water's all been boiled. We don't use table A7. We use another, we basically use tables 4 and 5 in a different way to substitute for table 7, compressed liquid water. Saturated ice, we don't use any of that. But then there's different properties, right? There's different refrigerant 134A. So if you ever go to Kelly's Automotive, or O'Reilly's Automotive or AutoZone, and you're now we're at the end of summer, and hopefully we don't have the really hot days, but when you go and try to recharge your air conditioner in your car, you can pick up a bottle of this stuff. It's a refrigerant called 134A, and it's the typical refrigerant used in air conditioners for cars. And so we need to know the properties for that material as a function of temperature and a function of pressure. Superheated refrigerant, and then we got a bunch of tables for air, nitrogen, oxygen, carbon dioxide. So you're building a rocket, or you need oxygen, right? You need to know the liquid ideal. Well, actually, this is ideal gas properties. Has nothing to do with liquid at this point. This is gas. All right. So, and then we do have the curves that I showed you, the bell-shaped curves in here. All right. So these are it. Again, for your test, when you do your test, go ahead and you can have these open. If you forgot what the density of something is, or right now we're not really talking about, you don't need to know this table, but sometimes you can come back here and you can have certain values that you might need. But anyway, don't worry about this for this test coming up. All right, I'll leave this open, but I'm going to go back to our. All right, so again, let's look at this bell curve that we just described. All right, so on the left-hand side, this is important. I'm going to go ahead and copy this and paste it onto. So this is what we call the saturation curve. And I'm going to highlight some important keys here, points. So this here, everything on the left-hand side. So everything on the left-hand side of the curve. On the left-hand side of curve. Shows, it says compressed liquid, but just say liquid region. Liquid only region. And then I could say this is also another way of calling it. So the liquid that exists in our rivers and streams and in the ocean, that's compressed liquid. All right. We don't think about it that way, but it is under atmospheric pressure, right? So if we lost atmospheric pressure, they would boil away, right? Remember I told you at I forgot what the boiling point is at but anyway, it would be somewhere around in the 20s or 30s, and so the especially in the summertime, the water will start boiling away if we lost all our atmosphere, right? So so the liquid that exists in atmospheric pressure is called compressed liquid. So anything to the left of that curve is compressed liquid. This is only a 1 point, but it's a very important point here. This is called, I don't want to erase maybe I'll just refer to it like this. That's the critical point. So what it is the critical point of a substance or liquid. It's the point, it is the point at which the substance can no longer be a liquid. So it turns out that, right, because this is a certain temperature here that this happens at, right? I think it's written here somewhere. Well, I'll write it. For water, it is 373. For water, the temperature is 373 Celsius. So in other words, you get water. The hottest. So this, in other words, this means the hottest temperature that I can to put to the hottest temperature that water can experience and still be considered water is 373 C. All right, I cannot. That is one point there, and it turns out that there's a certain volume that it has to be able to behave to. Right, there is a certain specific volume that this can happen. Right, and that specific volume here is a certain meters cubed per kilogram where that'll happen. And so if you go a little bit less than that, that means water, you can't get water even that hot. It's less than 373. But this is the highest point that you can actually heat up water, and it still could be considered water. The second you go above you go to 374, it's all superheated vapor. And so speaking of superheated vapor, that's this region here. So I'll just write it in red. Right-hand side of curve designates superheated vapor. In other words, everything to the right of the curve, the saturated line, is superheated. It's the superheated region. All right. So it's a gas basically. It's a gas that can have different temperatures, right? It's not associated. It's not a saturated vapor. It's a superheated vapor. And in here, so that leaves us with only one more area. That's inside here, and I don't like the fact that I used. Let's just call this. Let's go with blue. So inside the curve is a mixture. Is a mixture of saturated liquid and vapor. Remember you remember this one slide that I showed you here where there was some separation right there? Remember this here? That is you're in the middle of the curve there. You're underneath the bell curve there because there's some mass, there's some portion, some volume that's associated with vapor, saturated vapor, and some volume associated with saturated liquid. All right. These state 4 is an endpoint. Basically, it's on the curve. State 4 is on the curve. It's right before you start to go into superheated vapor. All right. All right. Very cool. So that's here, and that's it. So the tables in the back of the book, there's the saturated tables is basically it's everything that has to do with this bell curve here, on the curve and inside. Its values, and it's obviously it doesn't give you, because there's an infinity amount of points that go in here, right? Pretty close to infinity. So it doesn't give you everything. It just gives you like at certain, like at 5 degrees increments type of thing. So then you have to do interpolation in order to if you might have to do interpolation to get the actual problem, the actual exact value. All right. I would do an example problem, but my pen doesn't work, so I'm gonna have to let me see if I can just show you here. The example problem here in the book says, actually, let's do this real time. We only got a minute left, but I think the book says, find the volume VF. Okay, so when you're on this curve here on the left, the little f means liquid. Think of it as fluid, or it's a non-vapor, it's a non-gas fluid. Think of it more of a liquid. So that you got to find what is the value of VF at 90 degrees C. Okay, and that's saturated liquid, right? So what is VF there? All right, let's go to our tables. I'm going to show you how to do that. So for that, we go to our table. We're going to go to table A4, I believe, because we're given temperature. So let's go to A4. There it is. So table A4 is the table when they give you temperature. In our case, they gave us temperature, right? And they gave us temperature. Yeah, they did right here. Temperature was given to us, 90 degrees C. So let's go back to our table, and let's look at this. 90 degrees C down here. Here's 90. So at 90 degrees C, the saturation pressure at 90 degrees C is 70.183. So that means the pressure that if the water were to boil at 90, because this saturation table, this is a saturation table. It means everything here pretty much is seeing that those 5 states that we drew out. It's like it's at 1 atmosphere. Here's 1 atmosphere, 100 degrees C. The pressure is 101.42. That's 1 atmosphere. So it's basically the onset of boiling, right? So at 90 degrees C, we want to find VF, and there it is. So this is the specific volume. So it's in meters cubed per kilogram. If you look up here, meters cubed per kilogram, it's saying that at 90 degrees C, we have a specific volume of 0.001036. All right, if you grab this number, and then if you inverse it, right, the density, then it's close to 1,000, right? It's 1,036 or something like that. And that's basically the density of water at 90 degrees Celsius, you know, given this pressure for saturated water. This is water that's at its point of boiling. So there's the density. Okay. There's all these other properties, right? There's saturated vapor. Saturated vapor is this other part. It's here. It's right where it crosses on the right-hand side. So the specific volume there is going to be much larger, or the density is going to be much less, because that's at the point where it's turning into vapor, right? And there's that pressure, 70.183 kilopascal. All right. Now let's look at this right-hand side deal here. So it's saying, again, we find VF and find VG at 100 degrees C. This is in a piston where that's just exposed to the atmosphere, so it's 1 atmospheric pressure. And so I think this problem says find VF and VG at 100. And we know how to do that, right? At 100, it's right here. So it turns out that the pressure, let me just expose this. The saturation pressure is 101.42 kilopascal. And it's asking for VF, so it's 0.001043 meters cubed per kilogram. VG is 1.672 meters cubed per kilogram. That's for the vapor. That's the density of vapor. If you inverse that, you get the density of gas, right? And so of water gas, basically. And then all these other properties here's internal energy. So if you wanted to find the internal energy of anything, right, of a pure substance that's saturated, it means it's pretty much at its boiling point, but not any higher. Then here are the values: the liquid, the vapor, because remember it's separating. And here's enthalpy. We're going to talk about a little bit later. Enthalpy is the energy content of the pure substance, and entropy we won't talk until chapter 6. All right, so that was your example problem. This one here is in English units, so we won't cover. All right. And then there's the points in the middle that we'll use the next lecture. All the points in the middle, how do we calculate those, right? All the points underneath the curve. Everything that I showed you was pretty much just surprisingly, it was for just the outside, for the saturated liquid or saturated vapor. But how about the inside? How do we calculate that? I'll show you that next meeting. All right, so that's very important, because most everything we do is going to occur somewhere inside here. And it's something using an index that we call quality. That's how we determine. All right. Okay. Go back to any questions? Uh-oh, someone trying to get in. Okay. Oh, Dan, are you raising your hand still? Sorry.
Oh no, I think
long time ago. Sorry. You guys need to I'll try to learn to look at this, but I guess I can't lower your hand. But I usually don't, because it doesn't pop up. Can you explain how the freezing point is different again? All right. So the freezing point. All right. So yeah, freezing point. Where's the chart that gives us a freezing point? All right. So maybe this is the best thing to. The triple point here. All right. Triple point is where solid, liquid, and vapor happen, but because maybe that's not a good example. Actually, the triple point is what we use to calibrate our equipment. I mentioned it was the freezing point. All right, so let me go to that graph that shows pressure versus temperature. All right, so pressure versus temperature of water. All right, so this tells us right here that at 0 pressure and at 0 Celsius, then, right, at 0 pressure we have 0 Celsius, right? In other words, that's the saturation. This is just a saturation. This means that if you had liquid water, then it'll condense into solid. Actually, this is a saturation. This is a sorry. This is saturation curve between liquid and vapor. So actually, this doesn't tell us much, but what's happening is, yeah. So pressure. So water behaves. So the freezing point of water is always 100 degrees C, no matter how much pressure you apply to the water, and so that's so if you get water and you pressurize it to just say 10 atmospheres, right? That would be the equivalent of 140. Wait, so we got 14 psi is 1 atmosphere. So we go to a 1400 psi, or actually go further than that. Go to the bottom of the ocean, right? Go to the deepest part of the bottom of the ocean, and where the pressures of water are something like 100 bar, so it's like 100 or so times an atmospheric pressure. It's incredible pressures down there. So water will still freeze, just pure water, at 0 degrees C. Right. So if I was to get that pressurized water and then just bring it down to 0 degrees C, it'll freeze. The fact that we're pressurizing it doesn't change the freezing point. But however, it does change the vapor point, or the boiling point, right? Like this curve shows here. This is the boiling point curve for water. So it shows us that at 100 degrees C, water boils at, here should be like 101.3 kilopascal. So this is a function of pressure, temperature. Boiling temperature of water is a function of pressure. Freezing temperature of water is independent. It always freezes. So on Mars, which has much less air pressure or atmospheric pressure, water still freezes at 0 degrees C. So that means that, well, you can freeze at any. So I should say that's the yeah, that's its freezing temperature. Now you can freeze it at different temperatures, but its freezing temperature is 0 degrees C. I don't know if that makes any sense. Probably not. In other words, I can bring ice down to minus 100 degrees C, but I can't get liquid anything above 0 degrees C. If that makes sense? Because the freezing temperature of water is the same thing as the liquid temperature, the fusing temperature, I don't know what you want to call it, of water, right? The point where it goes from ice to liquid for water is 0 degrees C. So I can't have water that's minus 100 degrees C, if that makes any sense. I can't have cryogenic water. There's no way to do that. Now you could subcool water. Has anyone ever done that experiment where you get like a bottle of water and you put it in the freezer and you don't agitate it? You just kind of leave it there, and then you take it out and it's liquid, but it was in the freezer for 5 hours, right? And then you slam it on the table, and then it just crystallizes. Have you guys ever done that? Yeah, isn't that cool? Or beer, or whatever. I mean, that has to do more with nucleation of nucleation site or something like that. So it's basically subcooled liquid. I just contradicted myself, right? Because I said you can't get temperature of water colder than. That's one way you do it, but it can't. Everything we do here is the existence kind of like stable, right? So when the stable at 100 degrees C, the water boils, right? 1 atmosphere. It's kind of stable. Yeah, you could mess with the temperature a little bit, like in a transient way, like make it, but it's not stable. So anyway, that's one way of subcooling water, but it's not stable. right? It's just because you didn't give the water a chance to kind of nucleate its little crystals and form ice. It's kind of, if that makes any sense. Okay, I might have confused Isabel more than I helped. So sorry. Any other questions?
Yes, Professor.
Yeah.
I'm not sure if you explained it, but the reason why the saturated vapor point,
Yeah.
like for a pure substance, why it changes as the pressure rises. It's like, why does it keep skewing left? Essentially, is what I'm asking.
So you're talking about the you're talking about like this?
Yeah, slide 11.
Okay. So why does it? Okay, so we're increasing the pressure. Why are we, as we increase the pressure, why does this behave like this? So this is a physical, this is a kind of a chemical thing. I know that water, it has to do something with the ability of, you remember we talked about how the chemical nature of a pure substance is that liquid, if we pressurize the liquid, right, we can kind of offset its ability to turn into gas, right? So in other words, if just say we had gas, just say this is water, and we took it to 100 degrees C, and it goes from B to C, right? It turns into gas. If we pressurized it, just say to more than 1 atmosphere, then we're kind of forcing it to become a liquid again, right? In the sense, that's why this behaves that way. We're kind of forcing it. This part here, this flat part of the curve, that's the liquid part. That's the part where it's going from a gas to a liquid, and all the way on the left-hand side here is all liquid, right? But when we pressurize it, we're pushing towards the left. We're forcing. Otherwise, right, at this point here where my little cursor's at, if this was atmospheric pressure, we would be, I mean, sorry, if this was, if it was atmospheric pressure, we're so hot that we would actually be gas. But this high pressure forced us to be liquid, right? Or right here, saturated vapor liquid. I guess that's what I'm saying, is that the pressure kind of, in effect, forces the molecules to behave more like a liquid. Until we get to the critical point. At the critical point, you can't do any, the physics doesn't, right? The chemistry just says, well, that's it. I don't care how much you pressurize me. I'm never, you know what I mean? I'm never going to be a liquid anymore. And then at that point, it just becomes anything higher than that. And it's just superheated vapor. Yeah.
So the more pressure we have, the quicker it is to get to the boiling point with less volume?
Yeah.
Okay.
Yep. Now it flattens your curve here, that your distribution here under the curve gets shorter and shorter and shorter until the point you get to the critical point. At that point, you can't create liquid anymore, no matter how much pressure you have. So all pure substances behave this way. I don't know of anything that doesn't. The only thing that, because we're just talking about liquid to vapor, if we were talking about solid to liquid, water behaves weird in the sense that water is the only material that we know that expands when it freezes. Right. So, but we're not talking about anything weird like that. But all substances behave this way, right? They all have a critical point. They all get to a certain. When you pressurize them, they all want to be. You're offsetting the boiling temperature, or you're increasing it. All right, guys. At this point, I want to let anyone go that needs to go, and we'll just open it up for office hours. So, if anyone has any questions, I'd be happy to go over anything you want.
I had a quick question.
Yeah. Yes. Yes, sir.
I was just wondering why there's a volume increase from state 1 to state 2 when talking about the